let's basically review the part from the last lecture. We were talking about the limiting distribution of an irreducible ergodic discrete time Markov chain. So here we are talking about a Markov chain that is irreducible, which means that every pair of states communicate. And another way of saying it is that every state is accessible from every other state. And ergodic means that the states are positive recurrent and they are aperiodic. Okay, so in that case, Fij is equal to 1 for every I in J. So remember what Fij is. Fij is the summation of Fijn n from 1 to infinity, which is the probability that sooner or later I will be entered for the first time from J will be entered for the first time from I. And this is 1, which means that almost surely, J will be entered for the first time from I. And this is true for every I and J, including if I is equal to J. Okay, because all our states here are positive recurrent. Here you need, for this you need to be recurrent. Now, the general formula, there is, I told you before that there is something called the discrete renewal theorem, which tells you that the limit as n goes to infinity of Bij of n is Fij over mu Jj. And as you can see, that basically the right-hand side is generally a function of I and J. But in our case here, because our because our chain is irreducible and because every state is positive recurrent, Fij is equal to 1 for every I and J. So we end up with a right-hand side that does not depend on I. Now the right-hand side is just a function of J. And this means that, so basically here, if you think about this, what does it mean that you fix J and you make I change? It means that you are talking about the jth column in the transition probability matrix raised to the power n. So what we are saying here is that the jth column in p to the power n will converge to basically to be a vector whose components are the same. And they are all equal to 1 over mu Jj, which mu Jj, of course, is the mean recurrence time of state J. So it is the average number of steps that basically starting from J that you need to go back and enter into J for the first time after the initialization. Okay, so so this is an interesting thing. Again, you must keep in mind that basically that here we are talking about an irreducible ergodic discrete time Markov chain. Okay, now suppose that you start your chain again. It's the irreducible ergodic chain with any arbitrary distribution over the states. Okay, so according to some PMF, you basically initialize your chain. And we know that basically, unless you initialize with the stationary or invariant distribution, basically the discrete time Markov chain will not be a stationary random process. Okay, but let's examine what will happen when if our chain is irreducible and ergodic, and if time is and after a very large number of steps, specifically what happens as to the state distribution as n goes to infinity. Okay, so again, by tilde is just some initialization vector, and if you take the limit, then you are taking the limit of the TPM raised to the power n. Now, for our particular case, this is what the limit looks like. As we said, that according to analyzing this limit expression here, that Fij is equal to 1, the limit will depend only on J regardless of I, and this means that the jth column will just, so the first column, if our states are like 1, 2, 3, 4, and so on, then our first column will be 1 over mu 1, 1, 1 over mu 1, 1, 1 over mu 1, 1, and so forth. So what is the state distribution for a very after a very long period of time. Well, again, you multiply here, and basically what will happen, like if you take the first column, if you have this row vector times the first column, so it will be this times this plus this times this and so on. And so there is a common factor, which is 1 over mu 1, 1. And then when you sum, you basically sum the by tildes. And those will sum to 1. Okay, and so this summation is 1. It is a PMF. And then what if you do this to the second column? Again, 1 over mu 2, 2 will be a common factor. And then you have the sum. And that's 1. And so on. So basically what you get is this vector with the mean recurrence times. And in the last lecture, we proved that actually this is an invariant, right? So, if pi is an invariant or a stationary distribution, in our case here, because the chain is irreducible and positive recurrent, basically the distribution, the stationary distribution is unique. And this is basically pi 1 is 1 over mu 1, 1, pi 2 is mu over 2, 2, and pi 3 is mu 1 over mu 3, 3, and so on. So, right? So last time we basically proved this thing, that mu jj by j, this is equal to 1. So this is interesting. So for any Markov chain, if it has a stationary distribution, and you initialize it with the stationary distribution, it becomes a strict sense stationary random process, and the PMF of x1 and x2 and x3 and x4 and so on, basically every one of those guys will have the same PMF. It will not change over time. Okay. Now, what are the Markov chains with a stationary distribution? Well, those are any Markov chain that has a finite state space, or in the case of an infinite state space, then at least last time we have this theorem that if the chain is irreducible, then you just need one positive recurrent state, and you are guaranteed to get a basically stationary distribution. And if the chain is irreducible, and you know that it has a stationary distribution, then you are sure that at least one state is positive recurrent, and because the chain is irreducible, every state will be positive recurrent. Okay, but now we are saying something else. We are saying that what if you just initialize with any arbitrary distribution? So for this class of DTMCs, the class of irreducible ergodic discrete-time Markov chains, something very interesting will happen. So you start with any distribution, but you will converge. So after a large number of steps, okay, how large is large? It will depend on the chain itself. Okay, but after a large number of steps, what will happen is that the state distribution will converge to the invariant or stationary distribution of the chain. Okay, so even if you start initialize it in any distribution, then sooner or later you will find that the PMF is almost like the invariant distribution. Okay, but again, it is not like for any discrete time Markov chain. You need basically the chain to be irreducible. You need the chain to be ergodic. So it's a state. The states of the chain are basically a positive recurrent. Okay, so this is very interesting, rather very useful, right? So when you talk about this convergence to the steady state distribution, that basically the steady state distribution is the stationary distribution for those. It appears a lot in papers and so on. Then like you construct a discrete time Markov chain, and then you try to argue that basically it is aperiodic and the states are positive recurrent. Remember that basically for finite state spaces, the states are either transient or positive recurrent. You cannot have a non-recurrent state in a finite discrete time Markov chain, and you will basically make the argument in homework 13. So there is one problem in which I will tell you to basically rigorously show that if your state space is finite, you cannot have a non-recurrent state, but you can have transient states and positive recurrent states. And of course, if the chain is irreducible, then basically the recurrent states, once a state is accessible from them, it itself becomes recurrent. And so here we are talking about chains in which every state is positive recurrent. And note that we did it proof in the lecture that it cannot be the case in a finite Markov chain that all states are transient. So the only possibilities for a finite Markov chain is that either some states are transient and some are positive recurrent, or all states are positive recurrent. Okay, so let's now move to continuous time Markov chains. I will not spend, it will be just this lecture. And actually, we are not done with discrete time Markov chains. We will come back and do some special studies like random walks and stuff like this. Okay. So continuous time Markov chains. So Markov chain. So now we are used to this terminology. Markov chain, so it means that your random variables are discrete. So they take finite or countably infinite values. Okay, so it's Markov chain like discrete time Markov chain. So what is different now? The difference now is the index of the process. The index of the random process is no longer basically it does not belong to a countably infinite set. It belongs to an uncountably infinite set. Okay, so now T, so now x of t itself takes finite or countably infinite values, but our basically index, so the index of the process now is, so T belongs to an uncountably infinite set. And typically this will be the set 0 to infinity, the set of non-negative real numbers, okay? So now we have x of t. Rather than x of n, you have x of t. But x of t, once you fix a t, you have a discrete random variable. So that's the reason it is still a Markov chain, but it is continuous time. So here continuous time is a reference to the index of the random process. Okay, we still have the Markov property. I mean, we still have the word Markov, so we have a Markov property, and the Markov property here will be if you have t greater than v greater than u greater than or equal to 0, then the probability that x of t is equal to I, x of v is equal to j, x of u is equal to k, and so now basically t is greater than v, which in turn is greater than u, and now we are conditioning on these two guys, so the Markov property will tell you that actually this guy is not important. Okay, so it is, it is basically the same story here, that this conditional probability will exactly be equal to the conditional probability of x of t is equal to I, given that x of v is equal to j, and basically x of t and x of u are conditionally independent given x of v, so long as we have this basically progression of time instants. Now, basically, what is going on now? I mean, so a discrete time Markov chain is like a clogged system in which it moves in steps. So what is going on here, like when time is continuous? So what will happen if you enter into a state? Okay, so there is no longer like a clock. When you enter into a state, you can remain an amount of time, okay, that is exponentially distributed. Okay, so this is very important, and it must be exponential. If it's not exponential, then we do not have a Markov process. We will have something called the semi-Markov process, okay, which is outside the scope of this course. Okay, so you need basically the sojourn time. So this is the time that you remain in a state, or you wait in a state once you enter into it, is exponential. And every state can has its exponential value. So basically, this time here, Si, is exponential lambda I. Must be exponential. The parameter lambda I can vary from state to state. That's not a problem. Okay, and so basically, if you are like simulating this system, if you make a state transition and enter into a state, then you generate an exponential random variable with parameter lambda I. So basically, to know what time you will remain in that state, and after that you will make a transition to some other state. So you remain that time in a state, and then you make a transition out of the state to some other state. And why exponential? Because exponential is memoryless. Okay, and so I mean this is like very important here, and it's the only distribution that will work. Okay. Now, a side note is the following, that typically when you start learning probability and you take the famous or widely used random variables, the exponential random variable will be parameterized by lambda, and this lambda I is basically positive. But in the context of continuous time Markov chains, we will allow lambda I, okay, to be 0. So here lambda I is allowed to be 0. So remember that basically the expected value is, according to the notation we use here in this course, is 1 over lambda I. Okay, so we will allow lambda I to be equal to 0. And if we allow lambda I to be equal to 0, we are basically talking about an absorbing state, because like 1 over 0 is like infinity, and so like once you enter into a state, you remain there forever. Okay, so now this is, I make lots of mistakes, but this one is not a mistake. Lambda I is greater than or equal to 0. It is true that we allow lambda I to be exactly equal to 0 to indicate, if you are interested in having an absorbing state in your chain. And the meaning of the absorbing state is exactly like the discrete time Markov chains. Basically that it's a state, once you enter into, you are stuck there forever. Okay, and so the way of doing this is, you do not want like to change or anything. So basically you say, well, I will assume as if those guys have an exponential random variable with parameter lambda that is equal to 0. As in the discrete case, our focus will be homogeneous continuous time Markov chains. The transition probability, given x of v is equal to j, given that, what's the probability that x of t is equal to I? If you think about this, generally this will depend on the time instance t and v and the states I and j. So you need like something that depends on four parameters, I, j, and t and v. But for homogeneous continuous time Markov chains, you do not really care about the absolute values of t and v. What you care about is the time difference. So it will depend on I and j and the time difference between t and v. Okay, and sometimes I will not say the word homogeneous, but basically homogeneous is what we will do here. Okay, so now consider an infinitesimal delta t. And in that infinitesimal delta t, basically the events that can happen is that you remain in the state you are in, or you make one transition to some other state. Of course, if the time duration, if the interval of time you are studying gets larger, then you may have many transitions during that time interval. You may like make a transition from some state and then go back to the first state and so on. So here we focus on delta t that is small enough so that the probability of having more than one transition is basically negligible, and the events you care about for this infinitesimal delta t are remain as is, remain in the same state you are currently in, or make one transition to some other state. Okay, and relative to those events, any other event will have a negligible probability. Okay, so basically we will define what is BJJ of delta t. So this is the probability that after delta t units of time, after delta t seconds, you remain in j. So at time t you are in j, and then at time t plus delta t you are still in j. So what is this probability? It's the probability that the remaining time in the state, the time that you stay in the state, okay, is basically greater than delta t, right? So here you will see that I'm using Sj, which is this is the sojourn time. This is the time that you spend in the state starting from the time instant of entry. Okay, so if you look here, if you want like this probability, so this should be like a residual time, a residual or remaining time. Okay, because if x of t is equal to j, perhaps we have entered into state j 5 seconds earlier or something like this. But here is the nice thing about the exponential distribution. We don't care. So basically, suppose that you enter into a state, you remain there for a number of, let's say 17 seconds, and then you ask yourself, what is basically the PDF of the remaining time in the state? Well, it is still exponential lambda j. Here we are talking about state j. It will be the exact same thing. Okay, and that's the reason that we need actually the exponential distribution. We have seen when we studied renewal processes, for renewal processes, the residual or remaining time may be something very complicated. Okay, and so we need basically the exponential distribution so that we can do such type of analysis and say, well, we don't really, I mean, you look at something like this and say, well, shouldn't our probability depend on when we entered into state J? This is telling me that at time t it is J, but I mean it's J for the past 17 minutes or the past 2 hours or what? What is going on? We don't care. Okay, and so this is the nice thing about the exponential distribution. And so this is the probability that exponential lambda j is greater than delta t, and this is well known. This is e to the minus lambda j delta t. But because delta t is infinitesimal, I can write down this thing as approximately as 1 minus lambda j delta t. Okay, because delta t is very, very small, again, because we want to focus on a situation in which the possible events are either remain in a state or do just one transition to some other state. So the probability of remaining in a state will be 1 minus lambda j delta t. Now, what about the probability of going from state j to state I? So we will assume, so this is a matter of, we are defining what a continuous time Markov chain is, how it is constructed. So we will say that the probability ji delta t, so this is the probability of making a transition from j to I during a very, very, very small period of time, delta t, that we will take the probability to be proportional to delta t. It's linear in delta t, and there is a factor, a constant of proportionality, which I will call lambda ji, and this will be called the transition rate. It is so lambda ji is not a probability. The probability is when you take lambda ji and multiply it by delta t. Okay, so in that case, you will get a probability which is bji of delta t, and delta t is infinitesimal. Okay, so basically, if delta t is large, this formula will not make any sense. Okay, so this is something that is defined for infinitesimal time duration. So in a very, very short period of time, delta t, the probability of going from j to I is something that is proportional to delta t. And this is true. Okay, but what will distinguish between the states is that the transition rate, which is this factor of proportionality, will depend, generally it will depend on lambda j. What is I and what is j? Okay, so this is the transition rate from state j to state I, and it is a non-negative. So if it is equal to 0, you are basically saying that, during a very short period of time, you cannot make, any transition from j to I. So it can be 0 or positive. Now, suppose that you are in state j. Well, if you are in state j, by the law of total probability, these are your options. You will go to some other state, including j, remaining in j itself, right? So it should be the case that bji of delta t, like what we did in discrete time, that if you sum over I, you should get 1. What else? You are in a certain state. At another, after delta t seconds, you are in some other state. Perhaps in j itself again, which means that actually you are still in j, or you go to a new state. Okay, so isolate the term in which I is equal to j, and let's now write down basically, so bjj of delta t, because we are using the exponential distribution and delta t is small, then approximately this is 1 minus delta j delta t. Okay, 1 minus lambda j delta t. And remember, what is lambda j? It's the parameter of the exponential random variable characterizing the time that you spend in state j once you enter into it. And what are those other guys? By definition, those other probabilities all are proportional to delta t, and basically delta t is multiplied by something called the transition rate, delta ji. Okay, and so 1 will go with 1, and then you get to this, and delta t, you know, is some tiny positive parameter. You can divide both sides by delta t, and then you get this nice expression that basically, if you want things to make sense from a probabilistic point of view, you want something like this, right? Otherwise, you have nonsense. Then it must be the case that when you choose the parameters lambda ji, you know, you should choose them such that if you sum lambda ji for I not equal to j, you must get the lambda j, the parameter, you know, the sojourn time parameter of state j. Okay, so this is nice. As usual in mathematics, when you find that something is, you know, parameterized by two discrete parameters like I and j, then, you know, it's very tempting that you want to construct a matrix and to put those guys in a matrix. Okay, so basically we have those transition rates, and you know, it feels, you know, that they should be arranged in a matrix form. But the problem is that, you know, the way that we explain things is that lambda ji here is defined for I not equal to j, is defined for I not equal to j. So it would be like a matrix without a main diagonal, which does not make sense. And so what we will do is the following. We will define lambda jj. We will define lambda jj, okay, to be minus lambda j. So this is a matter of definition. Okay, so lambda jj, its meaning is, it's not a transition rate. In fact, it is non-positive. Okay, so it is non-positive. Okay, because it is the negative of the parameter of an exponential distribution. It is non-positive. Okay, and it is equal to minus lambda j. And now, if you look at this expression here, if you put lambda j, replace it by minus lambda jj, you can take the minus lambda jj and move it to the other side, and it becomes a plus, and then you can merge it with the summation to get something that looks like this. Okay, so here is the trick. So we started by saying, okay, how can we think about our, or how can we construct our continuous time Markov chains? So states, okay, states, a finite number of states, or a countably infinite number of states, and for every state you should assign an exponential random variable with a certain parameter that describes the amount of time that is spent in that state once you enter into it. Okay, and then you should also define lambda ji for I not equal to j, such that the probability of going from j to I in a very small time delta t is lambda ji multiplied by delta t. And then you say, well, are those transition rates, like, sort of, can I give them values regardless of, you know, the parameters of the exponential random variables? No, because again, to make sense, you must have that the summation over I of bij of delta t must be equal to 1, and you can use that to show that lambda j is equal to the sum of lambda ji for I not equal to j. But then you say, well, I mean, let's define this parameter lambda jj to be minus lambda j, and by doing this, you can now, so lambda jj now is defined, but its meaning is different from lambda ji for I not equal. So lambda ji when I is not equal to j means a transition rate. It is the sum, it is the thing that if you multiply by delta t will give you the probability of making a transition in an infinitesimal period of time delta t. But if I is equal to j, and so it's lambda jj, it is simply minus, it's the negative of basically the parameter of the exponential distribution of state j. And we will get basically that lambda ji is equal to 0. And so now, by doing this, you know, trick here now, every, you know, we can really take the lambdas and put them into a matrix form, and Now, if you fix J and do a summation over I based on this expression here, the sum is equal to 0. So now our matrix will be a matrix in which the sum of each row is exactly equal to 0. Okay? So any questions? Okay, so say welcome to the basically transition rate matrix, and it's given another name, which is basically the infinitesimal generator. Okay, so sometimes I use this, sometimes I use that. So it is the infinitesimal generator matrix, because basically this matrix, it has properties with another matrix P of T. We will see, like when we talk about the Chapman-Kolmogorov equation, and they form something in math that is called this a semi-group. Okay, and so so this word infinitesimal generator, it is like it's related to something else in math, but for our purposes, we will just use the name. And or a more basically relevant name is transition rate, not probability, In fact, what we have right now is that the elements of Q, the elements on the main diagonal, are non-positive. Okay, so they cannot be probabilities, right? So matrix Q, I will take the lambda I, lambda Ji, I will put them in this matrix. Now, the main diagonal elements are non-positive, and those are the negatives of the parameters of the exponential distributions. And the off-diagonal elements, those are the transition rates, those are non-negative. And now, based on this summation here, each row, it has a sum that is equal to 0, which means that if you multiply Q by the all one vector, then basically you get the sum of the rows, and so you get the all 0 vector. Okay, so you can think of the all 0 vector as 0 multiplied by the all 1 vector. So matrix Q has 0 as an eigenvalue. So remember, in discrete-time Markov chains, basically the transition the TBM, the transition probability matrix, it has 1 as an eigenvalue. It has 1 as an eigenvalue. Now we are talking about the Q matrix, and the Q matrix, the transition rate matrix, now it has 0 as an eigenvalue. Again, the difference is that in the other case, we have a matrix of probabilities, and the sum of each row is 1. Now we have a matrix, again, of rates as off-diagonal elements, and it contains basically non-positive numbers on the main diagonal, and the sum of each row is 0. And so basically now 0 is an eigenvalue. Okay, so suppose this is important, like when we, it's like very essential, the part I will explain now, very important, like when we solve problems. So it is like sort of a key ingredient in playing with continuous time Markov chains. Okay, so suppose that that one transition has happened from state J to some other state I. So what is this? From J you can go to some other, let's say that you can go to any other state, including I. So what is the probability that your transition will be to I itself? Okay, so specifically, to be specific, this is the probability that I'm interested in. So given, so what are we conditioning on? X of t is J. So at time instant t, we are in state J. X of t plus delta t is not J. So you are sure that at time t, you are in state J. At time t plus delta t, you are not in state J. So it means that you made a transition to some different state. So what is the probability that this other state, the state at t plus delta t, is specifically I? Okay, so we want to show that basically this probability is the ratio of delta ji, which is the transition rate, over delta jk, where k, where k is not equal to j. Which means that you take, you take a lambda, lambda gi, and you divide it by the other lambdas that are transition rates. Here you exclude lambda jg because, again, lambda jg is this fictitious thing. It is basically defined so that we can complete our matrix. Okay, so don't forget K not equal to J. And you know, again, things here like in many things in Markov chains, you basically apply Bayes, total probability, stuff like this. So here let's apply Bayes. So this is the probability in the numerator, this is the denominator. And so here in the numerator, we are saying that we have those three events, x of t is equal to j, x of t plus delta t is not equal to j, x of t plus delta t is equal to I. Well, basically, if these two events, you know, if these two events are true, you know, basically, so if you know that x of t plus delta t is equal to I, this guy here becomes its probability is equal to 1. Right, so you can do it like in slow motion, say that, well, what is the probability? I can write down this thing as the probability of xt plus delta t equals I, xt is equal to j, okay, which is written here. But then, I mean, if you want to do things again in slow motion, you will multiply by the chain rule, multiply by the probability that x of t plus delta t is not equal to j, given these two guys here. Now, you know, one of them is that x of t plus delta t is equal to I. So now again, we are talking about the case in which I is not equal to j. Given that x of t plus delta t is equal to I, which is not equal to j, then the probability that x of t plus delta t is not j, that probability is 1. Okay, so you know, again, like if it makes you happy, you can basically fill in this missing step in which I basically wrote down this 1, you know, directly. And then you apply the chain rule. So basically x of t is equal to j, then x of t plus delta t is equal to I. Okay, and you apply also the chain rule in the denominator. The difference is that here in the numerator we have I, here in the denominator we have not equal to j. And so here in the denominator, when I say not equal to j, so it can be I, it can be k, it can be v, it can be whatever, everything other than j. And so the difference will be that, so this will go with that. And basically we have these probabilities happening over an infinitesimal time. All of them can be written in the form of a transition rate multiplied by delta t, and so and delta t then will go with delta t. So you will have delta ji from the numerator, and in the denominator we will have the sum over the other lambdas. You know, sum over all lambdas, lambda jk excluding lambda jj. Okay, so this is lambda gi over lambda j. Remember that this thing here is equal to, which is, I mean, if it's minus lambda jj. Okay, so this again is very important in basically handling problems in continuous time Markov chain. Don't forget, this is again a question about something happening in an infinitesimal time. So you start in J, and after delta t, you are sure somehow that you made a transition, and then the question is, given that I was in J, and given that now after this delta t seconds, I made a transition, what is the probability that this transition is specifically to some state I? Okay, so it is lambda ji over lambda j, which is this summation here. Okay, any questions? We can, of course, there are Chapman-Kolmogorov equations, and again, like I talked about, like their derivation, sort of some details in the discrete time case here. I will just write it down that basically Big of t plus s. So what is this thing? This is the probability that, you know, so Big of t is the probability that in t seconds you will, you know, starting from I, you will end up at time t in state j. Okay, and it won't matter because of homogeneity. This is the same as probability x of t plus u is equal to j, given that x of u is equal to I. Okay, again, because the continuous time Markov chain is homogeneous, then what you care about is the time difference and not the absolute times. So Big t plus s. So what is this thing here? How can you interpret it? It's basically the probability that x of t plus s is equal to j, given that x of 0 is equal to I. And what you can write down this as a sum. So basically what you do is you sum over, so k in s, k in O, you know, basically the state space of the Markov chain. And so, you know, you go from I to j in t plus s seconds, you go from I to k in t seconds, and then you go from k to j in s seconds. And in the discrete time case, again, we showed that actually something, an expression like this, like it sounds very intuitive, but if you try to write it in detail, you will find that you need actually the Markov property. Okay, and of course, I mean, it may be you can rewrite down this thing as going from I to k in s seconds and then from k to j in t seconds. Okay, so what is important is that the sum of these two is equal to the sum that you have here. So here is the game that we will play, is that one, you know, so we have t and s, okay, and this is a general equation. What we will do is that we will replace one of them, let's say s, with an infinitesimal time. Why? Because basically we can compute probabilities easily. They are sort of by definition. By how the continuous time Markov chain is defined or is constructed, you can write down expressions for the probabilities once you are talking about infinitesimal delta t. So this is what we'll do here. I will go to this expression, which is general. I will replace s by delta t. Okay, so again, the benefit is now we have a probability of delta t, which I can write down explicitly. So you replace s by delta t, and then what you do is that you isolate the term in which k is equal to j, and so here k is not equal to j, and then you can write down, you know, so what is pk? J delta t, you know, this is actually how the transition rates are defined. Basically, this probability is lambda kj multiplied by delta t. So lambda kj, it is the thing that if you multiply by delta t, so that's the reason it's a rate, it's not a probability. You need to multiply it by something having the units of time. So lambda kg multiplied by delta t is basically this probability, and this is the probability that you remain in state j. Okay, and so this is 1 minus lambda j delta t, and don't forget that this minus lambda j can be written as lambda jj by definition. Okay, and so you do this, and you basically rearrange the terms such that, so you get bij of t here, you move it to the other side, and then this minus lambda j is written as lambda jj, okay, and then you have delta t and delta t, you know, and then you divide both sides by delta t, and it becomes clear what is the objective now. So the objective now is that if delta t goes to 0, we have the definition of a derivative, and we'll assume that this limit exists. Okay, so I will take it as a matter of faith that this limit exists, and so there is actually a derivative. Okay, of course, like if you do things rigorously, you need to justify why actually you even believe that this will converge to a limit. Okay, but here we will take it for granted that there is a limit. Okay, so we will assume the existence of this limit. And on the other side, again, the isolated term can be brought back into the summation, and so here again we will take for granted the existence of this limit or of this derivative. Okay, we will assume, and so basically we will assume that, you know, those probabilities are differentiable. Okay, so here let's actually also write it here, that basically assumed to be differentiable with respect to t. We don't have this differentiation business in discrete time Markov chains because the index of a discrete time Markov chain is, you know, something like 1, 2, 3, 4, and so on. But here it is tempting to basically, I mean, t, a time instant, I can have a time instant t and a time instant u, and I can make them as close to one another as I wish, right? So because the index of the random process is continuous, then we can play this game and we can take the limit as delta t goes to 0, and then we can ask about derivatives. Okay, and so you can again show this again. I will skip this, and it will result in this a nice expression. And let's look at the expression. It is dbij of t dt. Okay, and so you can think of this as, so you have a b of t. So this is a matrix This is a matrix whose elements are like B11 of t dt, B12 of d dt, something like this, B21 of t dt, dB22 of d dt. Of course, like the number of states actually may be infinite, but let's just write it like this. So you can, so basically this matrix will be written as dB of t by. So if I write something without the subscript, I mean basically the matrix and the derivative of the matrix here, it is just element-wise. I mean that basically you have the derivative of each element in the matrix. But what do we have on the other side? What we have on the other side, let's look here. So if this is I and this is J, this is IK and this is KJ, and this is a summation over K. So you see something like this, and automatically you note that this is how we multiply matrices, right? This is how we multiply matrices. So basically this expression here, if you want to write down all the derivatives in just one expression, this means that d of p of t, so this is the guy containing all those guys, dt is equal to this. So it is p of t, and what is the matrix containing the lambdas? Q. So this is basically in a compact form all those guys. I mean, because those guys are for I and J, and again under the assumption that basically all those probabilities are differentiable, which again is something that is proven. So it is not like I'm skipping the proof. It's not like there are cases in which this will not happen. It will happen always, like, but I skipped the proof. Now you can play the game of the Chapman-Kolmogorov basically equation, but like here we put this guy equal to delta t and this is t, but actually we can put delta t here and we will reach another equation which is like this one here, but it will be also, so also we have, now we have this summation, and this summation, if you read it, summation, so I, J, K, and K, and summation over K, right? So remember, if you study matrices and you multiply matrix omega by matrix gamma, okay, and this is equal to C. What is Cij? Cij, take omega ij, omega ik, and then you take gamma kj, right? Ij, ik, kj, and then you sum over k. So basically you see something like this. Okay, oh, this is a matrix multiplication, and what we have right now is Q B of t. Okay, so by basically playing with delta t, you can put it here, or you can put it there, you actually can get these two expressions. So actually this is a proof. So this is this shows that Q and B of t commute. We know generally for matrices, if you have the class of of n by n matrices, then those guys, AB is not necessarily equal to BA, but our proof actually shows that B of TQ is equal to QB of T. So basically changing the basically the order, putting one first before the other. I mean, it will not change in our case here. So we say that these two matrices, P of T and Q, they commute. And so what is this? I mean, what is the idea here? What is this about? Writing a differential equation? Yes, exactly. Writing a differential equation so that you can solve it and so that you can get an expression for P of T. Okay, so again, the problem is, what if I ask you something like this? Bij, what is Bij of T, which is the probability that X of t is equal to j, given that x of 0 is equal to r. What is this thing? Can we write down an expression for it before doing this page? No. I mean, because the definition and the construction of the continuous time Markov chain is concerned with infinitesimal times delta t. So the idea is that, if I have something like this, Bij of delta t, and j is not equal, I can write down this as lambda ij of delta t. but I don't know what to do if delta t becomes not infinitesimal. Okay, so the trick here is to do this. Write down the Chapman-Kolmogorov equation, okay, and then make one of the time variables is delta t, because you know how to write down those guys in terms of the transition rates. So what do you obtain? What I obtain is a differential equation, actually a big family of differential equations. So basically every element in this matrix is equal to some element in this matrix product. So we have all those differential equations. And if we can solve those differential equations, then the nice thing is that we will have P of t. Now for every t. So this is basically the idea, is how to use the Q matrix, and how we define things for an infinitesimal time, so that we get the transition probabilities for any arbitrary time t. Okay, so we can solve this, these differential equations, and this is the solution. So the solution is a matrix exponential. P of t is equal to e the qt, t is greater than or equal to 0, and this matrix exponential is a shorthand for this. So when you solve, I think I will do like a partial proof on the next page, that basically you solve, you get a Taylor, something that looks exactly like the Taylor series of the exponential function. So you define something called the matrix exponential, right? And I'm sure that like you encountered this before. If not in probability or random processes, then also you encounter this in a course on signals and systems, a course on control, and so on, because like this thing also appears like in control systems. You have continuous time systems are characterized by differential equations. I'm talking about linear systems, and again you find yourself have equation that looks something like what we have here, but it's written not for probabilities, it's written for the states of the system, and you get this matrix exponential. So like I will talk about it on the next page. But there is there is the what I need to emphasize right now, that good news, basically you can now talk about those guys for any arbitrary t, and unsurprisingly it turns out that you will need q, right? So basically to be able to find those guys you will need q, and you need to do this specific matrix operation, as we'll see why actually you get this summation here. Okay, so the solution is a Laplace transform. Okay, and basically the solution is general, so the solution is correct, but the problem is that to do the solution you need like to write down to write down q as a matrix, and then some nice matrix, and then the inverse of the first matrix, okay, so that you can proceed with the proof. So a candidate can be eigendecomposition, so you can do the eigendecomposition of Q, but unfortunately not every n by n matrix is diagonalizable, and so there are matrices in which like you cannot write them. So basically this is the sweet case. So the sweet case is that I will assume that Q is, it has an eigendecomposition, so Q is epsi omega epsi to the minus 1. Okay, so that's and so omega is like a matrix, a diagonal matrix of eigenvalues, and in that case basically the any power of q will be basically the same thing, but with the diagonal matrix basically its elements will be raised to the power k. But again the deficiency in this, what I'm doing here, is that many good and useful matrices are not diagonalizable, and if they are not diagonalizable you can still proceed with the proof, but you will need to do something called the Jordan canonical form, okay, which is like sort of a generalization of this expression here, but the matrix of the Jordan canonical form is actually not diagonal. Okay, it's not diagonal and nice like this matrix, and for simplicity here I will focus on the diagonalizable Q matrix. And the idea is you take the Laplace transform, so the Laplace transform of this thing of derivative, it's s multiplied by the derivatives, and then you need to subtract the initial values, and I will assume that the initial values are basically, so Pii of 0 is equal to 1, Pij of 0 is 0 if I is not equal to j, okay? Which is something like similar to what we did in discrete time Markov chains. We defined Bjj of n to be equal to 1 when n is equal to 0, right? So it's exactly the same thing here. And this one, take the Laplace transform, then basically take this to the other side and take Bs as a common factor to, so this is a matrix, take it as a common factor to the right. And then, assume that this matrix, is invertible. Basically, you move it to the other side, and then you get this expression here. Now, assuming that the matrix is basically invertible. Now, the issue is that, this seems like pointless because, okay, so what is this thing? So when you use the Laplace transform to solve differential equations, again, like here, so what is this thing in the time domain? So this is where we need like Q to have a nice eigen decomposition, or, if not, we will use the Jordan canonical form. So basically replace Q by its eigen decomposition, and then this I here, this identity here, write it as ipsi inverse, okay, which is the ipsi inverse is identity, and then take ipsi as a common factor to the left, take ipsi inverse as a common factor to the right, and in between there will be S identity minus omega, which is a diagonal matrix. Okay, so we'll have, then if you want to basically take the inverse, okay, the inverse will be the inverse of this guy, which is ipsi, the inverse of the diagonal matrix. Well, that's an easy inverse. Basically, you go to each main diagonal element and then flip it, take the reciprocal, and then ipsi will be ipsi inverse like this. And you do the inverse Laplace transform. Basically, this is the Laplace transform of an exponential function. Okay, and so this is the inverse Laplace transform will be basically those exponentials here. You get those exponentials here. Okay, and those exponentials. So again, this is a valid form for P of t, but we can do more. Those exponentials, they have a Taylor series, so you can write down things as a Taylor series. And then what you can do is that you can split, so you can split the Taylor series expansion into the ones, identity, and then into omega multiplied by t, then omega squared multiplied by t squared multiplied by 1/2, then omega cubed multiplied by t cubed divided by the factorial of 3, and so on. Okay, so the idea is that this, you can say that we are done here, but you can do something else, which is do the Taylor, those are normal exponentials, do the Taylor series expansion, and then split, so write down things as, as 1, and then this, which, when as a matrix, this will be identity, and then omega t, and then this guy. And so that's the reason that you get this Taylor series, but it now includes a matrix. It now includes a matrix. Okay, and then you multiply by ipsi and ipsi inverse, and so this will give you identity, and then with omega, this will give you back your Q. The idea is like you want to express P of t. In the differential equation, we have matrix Q, so we want like to explicitly have our result in terms of Q, and so this is how we do it. And so you get, so the solution is this series, which looks like the series, the Taylor series, but involving a matrix. So we will define something called the matrix exponential. So the matrix exponential, like in MATLAB, it is EXPM. And note that it is different from, so in MATLAB, if you have a matrix A11, A12, A21, and A22, if you apply exponential only, then it is an element-wise operation, and so it will be e to the E11, e to the E12, e to the E21, e to the E22. This is not what we are doing here. Matrix exponential means something else. Matrix exponential, XPN, means that you will take this matrix here, you will take identity, okay, and then you take this matrix here, and then you take 1/2, and then the matrix is squared, and so on and so forth. Okay, and so it is a different animal, and And basically, I think like if I ask you to do matrix exponentiation in this, most likely it is something that is either we are talking about 2x2 things or something that for which you can use MATLAB. So don't worry. I mean, and of course, there are like lots of issues here about convergence. I mean, once you get something like is infinite like this, so does it converge? Will things depend on whether your chain has a finite state space or infinite? So in the discrete time case, we show that actually infinite chains they can behave like different from finite. But in continuous time Markov chains, we will not basically talk a lot about these things. It's it's just everything will be I will avoid controversy like in the questions. So no tricks like regarding convergence or so on. Okay, there will be like a question. I will ask you a question about to prove a convergence, but it's not actually a question about matrix exponentiation, or it does not require actually like things related to the Laplace transform here. Okay, so so this is our master, so P of t. So again, don't forget what is this thing. This is a matrix in which you have Bij, of t, and what is this thing? It is the probability that x of t is equal to j, given that x of I is equal x of 0 is equal to I. Okay, and so it is matrix, and it can be an infinite dimensional matrix if you have an infinite, countably infinite number of states. And now we are saying that this is equal to this guy here. And what is the Q matrix? It's another matrix. Okay, so the matrix P of t, it's basically a Markov matrix. So so basically the sum of each row is equal to 1. Sum of each row is equal to 1. The elements are probabilities; they are non-negative. And the Q matrix is a rate. Okay, so this is a transition rate matrix. And now what is lambda? What is lambda ij? Well, if I is not equal to j, then lambda ij is this thing. So basically it is what gives you this probability, lambda ij of delta t. And if the two indices are the same, then we are talking about the negatives of the exponential random variables, describing the times that you spend in a state once you enter into it. Okay, and what is this fanciful thing? Well, it is basically a series that hopefully it will converge. Sometimes so this is like if you have Q, this is how you obtain P of t. But sometimes I will give you P of t and you need to obtain Q from it. Okay, so in that case, you can do it in a number of ways. And one nice way is to take B of t minus I over t. Okay, and so this will give you, take the limit as t goes down to 0, this will give you Q. Okay, so this will give you the matrix Q. And the reason for this is that you can write down basically okay, so here is the reason. If you take B of t minus identity and then you divide by t, what do you have? What do you have from this series? Assume again that the series makes sense and it converges and so on. So if you take I and join it to P of t and then divide by the scalar t, you have Q. So Q now is living alone, plus. And then you have 1 over 2, and then you have Q squared. But then the scalar t squared becomes t, and then you have 1 over 6, and then you have Q cubed, and then t squared, and so on. Now take the limit as t goes to 0. And now again, there are issues because this is an infinite sum, but assuming that we can take the limit term by term, this will go to 0, this will go to 0, everything will go to 0 except for Q itself. Okay, so that's the reason behind this expression here, that you can obtain Q from P of t using this limit. Okay, so this is very important, that because these are now like in discrete-time Markov chains, it's like the hero is the TBM, and basically the transition probability in n steps, it's just the TBM raised to the power n. Now we are talking about like sort of two things. We are talking about Q and B of t, and again P of t is equal to e to the qt, and t is greater than or equal to 0, and Q itself is limit as t goes to 0 of B of t minus identity over T. Now, B of T is, I emphasize, it's a Markov matrix, which means that, you know, it is like a transition probability matrix. It is like a power of the transition probability matrix in the discrete time case. It has an eigenvalue, it has an eigenvalue of 1, stuff like this. You know, is there a left eigenvector for P of T? Well, there is a guaranteed left eigenvector if the number of states is finite. So these things can be said about P of T. But we have also this nice function Q, which is again not a matrix of probabilities. It's a matrix of transition rates and then of the negatives of exponential parameters on the main diagonal. The sum of each row in Q is 0. The sum of each row in P of T is equal to 1. Any question? Now, do we have conversions? Like BI, you know, so remember that in the discrete time case, this was like the beginning of the lecture and the end of the previous lecture. We have something like this. Do we have something the same here? Yes. And of course, you need. It's not for every continuous time Markov chain. You know, you need those guys to be irreducible, and you know the states to be. So can we do state classification? Yes. Okay. So I will, but I will not ask. You know, I will not ask you about classifying the states of continuous time Markov chain. But it is sort of the same thing like discrete. So there are, you know, transient states. Recurrent, positive recurrent, non-recurrent states, and so on. So you can basically do the same thing, but I will not give you any question actually regarding classifying the states of a continuous time Markov chain. And if I give you a continuous time Markov chain in which, like, I ask you like to study this limit, you know, then it is basically a Markov chain that is irreducible, which means that every state is reachable from every other state. And it is, you know, and it is positive recurrent. So, in other words, basically, you have a limit. This limit will exist and it will be well defined. You need to worry about it. You just need to obtain it and play with it, as you will see in homework 13. Okay, so so yes, I mean you can have a limit, and this limit, you know, so it's Bij. It may depend only on J, not on I. Okay, so the limit may depend only on basically on the second index, the state to which you go to, and not on I. And again, suppose that our chain, it has this steady state. You know, you can take the limit. There is a well-defined limit as t goes to infinity. So so what is basically, what can we use this for? In many cases, like in applications specifically, so whenever the continuous time Markov chain is used in, I have seen it like used in wireless communication, say that, you know, typically it is the interest like steady state. You know, steady state is like sort of what we focus on. So doing things with limit as t goes to infinity. So the idea is that, so this is one of the equations that we derived from the Chapman-Kolmogorov equations. And now take the limit of both sides. Take the limit of both sides, and now assume that the limit exists and there is actually steady state. So steady state, it means what it means, right? Steady state means that things, variations over time will become negligible. Right, so if I tell you that there is a function of time that, you know, converges to some constant value, then, you know, it means that after a large, you know, period of time, basically the function will be like within epsilon from its limit, and you know, you can just assume that the function basically is no longer changing. The changes in the function are basically negligible if there is a limit, and we will take the existence of the limit for granted. Okay, and so basically, if you know have a limit, this thing will be equal to 0, and then you have a limit of summation, and let's assume that we can take the limit inside. Now this is guaranteed to be true if you have a finite state space. Okay, so if you have a finite state, you do not even need to justify this thing. It's basically the linearity of limit. But if you know, if you have an infinite number of states, then basically this thing needs to be justified. We will not do this here. We will just take it for granted that we can take the limit inside. And if we take the limit inside, then we have this limit here, limit t goes to infinity bik of t. Okay, and as I said, that basically we will assume that this limit exists, and it depends only on k and not on I. So you go from I to k, regardless of the initial state. Regardless of what you start in, basically you go to some some number that depends only on k. Okay, so this will be pi of k. Okay, and convergence is to, again, like the first page in this lecture, if there is convergence, it is actually to the stationary distribution. So I just wrote down things in terms of pi. Okay, so what is our equation now? I mean, this is like in applications, most likely you will do the steady state. And now this is the equation for the steady state. So again, you start with, so let's do exactly what happened is that you start with the Chapman-Kolmogorov. Okay, Bij of t plus s is equal to summation k Bik of t Bkj of s. Then you replace this guy, you set s equals delta t, and then you use your knowledge about the probabilities for infinitesimal time durations, and from this you get the differential equation, which is Bij of t dt is equal to summation k Bik of t lambda. Okay, so those are the elements of the Q matrix, lambda kj. Okay, so this is the differential equation. Then so one thing is to solve the differential equation and get explicitly Bij of t as a function of time. So this is, in some cases, we are also interested in getting this as a full function of time, but sometimes we are interested in the limit as t goes to infinity. In that case, you take the limit of both sides. Since things are assumed to go to steady state, then this guy becomes a 0, so limit t goes to infinity. And we'll assume that we can interchange the summation and limit, and there's infinite, we can, yes, infinite sum and limit. So if it's an infinite sum, again, like you should not worry if this is a finite sum. Then you take the limit as t goes to infinity, Bik of t, and this thing will be assumed to be something that depends only on k, and we get this basically expression here. So this is the steady state distribution, assuming that we have those limits that they exist and so on. And the fact is they do not exist for every continuous time Markov chain. Like for the discrete time case, also you need this irreducibility thing. You need the fact that basically every state is reachable from every other state. Okay, you need things that the states being positive recurrent and so on. Now this is a very important equation. It's called the global balance equation. Okay, and so this is also, if you look at it, you can write it down also. You look at down, it's summation pi k lambda kj. Again, since our work in Markov chains, now we are used to see these terms here, and this is, I can collect the pi's in pi vector, row vector, and the lambdas in q, and this is pi q is equal to all 0 vector. Okay, which I can write as pi q is equal to 0 multiplied by pi. So again, remember q, it has an eigenvalue of 0 because the sum of each row is equal to 0, and q, if it has an eigenvector corresponding to 0, and this is like guaranteed it's guaranteed for the in the finite state space case. And if you have irreducible chain, it will also be guaranteed in the infinite state space case once you have at least one positive recurrent state. Okay, so you will find the vector by it's a stationary or invariant distribution, and by the way, this will satisfy, if you examine the relationship between q and p of t, this will satisfy that pi p of t is equal to 1 pi. Okay. And for the chains in which you go to steady state, basically regardless of your initialization, you will converge to the stationary distribution. And so you get this steady state by obtaining the stationary distribution. And the stationary distribution for continuous time Markov chains, now, again, it depends on the situation you are in, but in many cases, we obtain the stationary distribution using the Q matrix itself, pi q is equal to 0 pi. So the difference is that for discrete time Markov chains, it is pi p is equal to 1 pi. Now it is pi q is equal to 0 pi, or pi q is equal to the O0 vector. So you can do this. You can write down things in terms of matrices, or you can write down things in terms of a summation like this. And this sum can sort of be written in sort of an intuitive way. I can split the term corresponding to k equals j, and basically this lambda jj can be written as minus lambda j, and I can move this term now with the minus sign to the other side by j lambda j is equal to this sum without summation over j, and then lambda j itself from basically the first page on continuous time Markov chains is summation lambda jk for k not equal to j. Okay, and so you get basically this expression here, which can be thought of as an eigenequation for q. It can also be written as this form: by j multiplied by summation k not equal to j lambda j k is equal to summation k not equal to j by k lambda kj. Okay, so what is this thing? Let's look first at the right hand side. So this is a summation with an index that sweeps through all states except state j itself. So k is a state that is different from j. And so what we have here is by k, so that's the steady state probability of being in state k, and this probability is multiplied by the transition rate of going from k to j. Remember that infinitesimal duration of time, the probability of going from k to j is lambda kj multiplied by delta t. So this is like pi k multiplied by lambda kg. So this is like you sum over all other states. You take the probabilities, multiply them by the rates. So this is, you can understand this as if it's like the overall rate of entering into state j from any other state. So this is the right hand side. The left hand side is by j, which is the steady state probability of state j, and it's multiplied by this sum, which is the sum, which gives you the rate of making a transition to a state other than j. So this is like going out of j. So it's like the rate of leaving state j is the rate of entering state j. So it's like the balance or equilibrium equations that we encounter in things like physics and so on. So the rate in is like the rate out. Rate in is like rate out, and this is another. So like to get the to get a stationary distribution or to get a steady state distribution for a continuous time Markov chain that has a steady state distribution. Again, you can think of the problem in a number of ways. One of them is an eigenequation for the Q matrix, pi q is equal to 0. And this corresponds to this equation here, or you can do just a bit of manipulation and write down things in this form here, the so-called the global balance equations, again, which is sort of, it has like a nice interpretation. Like again, in basically one side will have the rate out of the state, and the other is the rate into the state, and of course each rate is weighted by the probability, the steady state probability of the state. Okay, so those equations again are famous, and they are called the global balance equations. Okay, and again the steady state vector is a vector satisfying by q is equal to 0. So this is like the result at the beginning of the lecture. So the limiting distribution also for discrete time Markov chains, it was basically one of the invariant it was the invariant distribution, again, because this happened in a particular class of chains that have like a unique stationary or invariant distribution. Okay, so an example of you know, there are so many examples for this continuous time Markov chains. So most likely in the next lecture I will give you the last page, because I don't think I have time for it now. So it is like how to actually like have a system and model it using continuous time Markov chains. Okay, and this will require that you construct the Q matrix by hand. You do it yourself. You read the problem carefully, and you change the, you know, you translate the information in the problem into basically entries into the Q matrix. But here I'm giving you a process in which the Q matrix is given, and the Q matrix here is sort of tri-diagonal. And so basically in each, the first row it has 2 elements that are non-zero, but every other row it has like 3 elements. If there is a last row, the last row also will have 2 elements. Okay. So what is the meaning of having a structure like this? So you have a state I, you know, to have this structure that you see in front of you, it means that from a certain state I, you know, you can go to I plus 1, or remain in I, or to go to I minus 1, and that's it. You cannot like directly go to I plus 2, or go directly to I minus 2. I'm not saying that I plus 2 is not accessible from I, it is not directly accessible. Okay, so basically the transition rate is equal to 0. Okay, so a birth-death model is a specific class of continuous time Markov chains that makes our life easier by constraining the possible transitions, by saying if you are in a certain state, well, you may remain in that state, or you can make just 2 out of state transitions to I plus 1 or I minus 1. So in one case, you know, the state increases, the other case, so this is like birth, and in the other case the state it's becoming less, and so it's like death. It's called this. Okay, I don't know the historical reason it is called birth-death process, but actually, you know, here the increase is called birth, even if we are counting death. Okay, so so don't take things too literally. So birth here, it means that the state increases, death means that the state decreases. But I mean, I think there will be one example in the homework 13 about about like an epidemic or something like this. So so again, this is a very special process that is very useful. And guess what? Like a Poisson random process is a special case. It's a special case of a birth-death continuous time Markov chain. So you see the Q matrix, and then you say, okay, it looks like a good Q matrix. You know, it satisfies what we know about the Q matrix. You know, the main diagonal elements are non-positive, and the elements on the main diagonal should be the negatives of the exponential random variables, basically the Sojourn times of the states. And then the off-diagonal elements are non-negative, and every row sums to 0. Now the question is there a stationary distribution, an invariant distribution? Well, let's try our luck with the eigen equation, pi q is equal to 0. So what you do is that you write down, you know, you write down this thing and you multiply by pi, and here I am taking the states to start from 0. Okay, so you have pi 0 by 1 by 2, right, this, and on the other side you equate with the all 0 vector, right? So not the pi vector like in the P matrix case. And then you start basically saying, okay, so this multiplied by the first column, so this is minus lambda 0 by 0 plus lambda 1 mu 1. Okay, so this should be equal to 0, and then you get pi 1 in terms of pi 0. And then you take the vector and you multiply by the second column, and then you get an equation that relates by 0 by 1 by 2. But remember that actually pi 1 is already in terms of pi 0, so we can use this equation to express pi 2 in terms of pi 0, and you will get this expression here. And you can keep doing so. Perhaps you can confirm by induction that basically pi n is pi 0 multiplied basically by the product of lambdas and mu's, and those are the lambdas and mu's that appear basically on the diagonal above the main diagonal and the diagonal below the main diagonal. Okay, so you will get basically this expression here, and then you say, well, if those are really probabilities, their sum should be equal to 1, and so you try to sum them, but of course in the general case this will be an infinite sum, and so well, we have a stationary distribution if actually this summation converges. Otherwise we don't have a stationary distribution. So in the case that this summation converges, then basically you can it will be a finite number, and you can take pi of 0 as a common factor, and then the other side will be 1 over 1 plus this finite number. So we will need basically this condition to be true. Now, if all lambdas are the same and if all mu's are the same, basically this thing is lambda to the n over mu to the n. Okay, and so the condition of convergence, the condition of having a stationary distribution, will be the product of lambdas. So that's lambda to the n over the product of mu's, that's mu to the n. And so for this to converge, you must have lambda to be strictly less than mu. So the moral of the story, for a birth-death continuous time Markov chain, a birth-death model, basically there should be some condition on the lambdas and mu's so that you get a steady state or a stationary distribution or invariant distribution. And typically what you do is that you solve the eigenequation, and typically you will have like to get like you express the probabilities in terms of one of them. Typically it's like pi 0, and then you say, well, I mean, if those are really probabilities, their sum should be unity, and then you try to do the sum. In the finite case, there will be no problem whatsoever. In the infinite case, you will find basically that there are conditions, okay? That there are conditions that must be satisfied so that you have basically a vector of a PMF, a vector with non-negative entries whose sum is equal to 1. Okay, and one process is basically it is the special. All the mu's are equal to 0. All mu's are equal to 0. So all those guys are equal to 0, and the lambdas are equal to -1. So basically, the Q matrix of a Poisson process, it looks like this: minus lambda lambda, minus lambda lambda, minus lambda lambda, and so on. And it is only a birth model because it is an arrival process. It is a counting process, right? So basically, in a Poisson process, how do we know that this is actually a Poisson process? Let's see. You start in state 0. What is the meaning of the first row here? The meaning of the first row here is that, the state 0, it has an exponential distribution basically with parameter lambda. So you stay in state 0 with, basically with exponential lambda. And then what do? And then after that, you make a transition, and the only state to which you can make a transition from 0 is to go to state 1. Now you are in state 1. Okay, so here you are in state 1. So what is the meaning of this minus lambda? It means that once you enter into state 1, you remain in that state for an exponential duration of time, and then after that you do that, you go to some other state. But by construction, the only other state to which you can go is state 2, and so on and so forth. So basically, the sojourn time of every state is exponential with the same parameter lambda. So it is as if we have the inter-arrival times are all equal, are all exponential lambda. And they are IID, they are independent of one another, and so that's the Poisson process.